Okay, so welcome everyone. Thank you for being here, and also thank you to the organizer to let me speak to you today about MACE. And of course, the work that I will be presenting is not done by me alone, so I also want to thank my collaborators, which are Frederik Keuster, Marie van der Zande, and also my supervisor, Leen de Sin. This talk might be a bit more technical than the previous ones, but I'll try to guide you through it as good as possible. Let me first still go over the context a little bit. So we've seen these type of observations already a few times yesterday and also today. So we here see observations of AGB outflows, and we clearly see that these are not nicely spherically symmetric as we have long been thinking, but we see these complex structures that we believe are due to the gravitational interaction with a hidden companion in these dusty outflows. Now, if we want to get the full picture and also model properly the mass loss rates, they depend on these structures, of course, and not only in a spherical framework. We need to now take into account these companions. But if we want to get the full picture, we really need to model the hydrodynamics as well as the chemistry. Also, of course, some radiative transfer, because of course, what we observe here is the emission of these molecules. Thanks to the talks already today, the one from Shazreen this morning and just the one now from Marcelino, you got already a broad introduction into the hydrodynamics and also the chemistry. But let me just quickly go over it again. So we already have very nice hydrodynamical simulations in 3D from which we learn quite a lot already, as you've heard this morning. And also here I show you such an example of such a model of an AGB outflow, and I show you the view in the orbital plane and then perpendicular towards it. And we again retrieve these spiral structures that the cross-sections show these arc-like structures. So we really need to do this hydrodynamical modeling in 3D, as we can see here. On the other hand, we also have already nice chemical models, but they stay pretty much in a one-dimensional framework, as also Marie has been telling you yesterday. So what you can see here on this plot, so it's again some abundance profiles as we've seen before, but in this time I change the density of the outflow and also the temperature. So the density is given on the left and the right side, and then the color indicates different temperatures in the outflow. And for two species I give here as an example, you can see that depending on these physical parameters in the outflow, really these abundances change. And hence we expect that because of the spiral structures we see in the outflows, also this will impact the abundances. So we have these two separate components now, but actually we want to merge them together. Of course, this doesn't exist really up until now, so we don't know how this looks like, but this is actually a bit the aim of what we've been trying to do. Of course, with every aim comes some problems. And in this case, the problem is that all these things are computationally very slow. As you probably know very well, hydrodynamics takes a lot of time. It's very expensive, computationally speaking. And if we then also want to add chemistry towards on these computations and try to do this on the fly, so in every time step in the hydrodynamical model, this will just become computationally infeasible to do a thorough parameter study for all of these AGB stars. So hence we need to overcome these issues, of course, and that's why I introduce you today to MACE, which stands for a machine learning approach to chemistry emulation. And so the work that I will be presenting now, it's recently been accepted for publication and it's already on arXiv. So if you are interested and are enticed by what I will tell next, please go visit the paper already. So now what is the aim of MACE? So I already explained it a little bit. We want to now find a way to overcome these computational difficulties, and we will do this by building a surrogate model for the chemistry. Let me first remind you a bit, or maybe introduce you to chemical kinetics. So how do we generally do this? So we start with some physical setup, which are just the physical parameters, so given by the density, the temperature, and also some information about radiation. And then we start off from a set of abundances. If we evolve this using chemical kinetics, we can then predict the final state of these chemical abundances at some later time step, delta t, where generally in the basic formalism, we keep the physics constant. Now what actually happens, too quick. So chemical kinetics is basically solving a set of coupled ordinary differential equations, which look like these. So we have the change in for a certain abundance, or for the abundance of a certain species, and this is given by the difference between the production and the destruction reactions. Now, if we're considering a chemical network that only consists of 1 and 2 body reactions, which is generally the case in AGB outflows, this equation reduces to sort of a second-order polynomial differential equation. So we can solve this, and then we know the evolution of the chemical abundances. However, of course, if we are dealing with a pretty large chemical network, for example, of about 400 to 500 different chemical species, we get a coupled set of these about 500 differential equations. So that's already also quite expensive to calculate. So we want to overcome these expensive calculations by the use of emulation. And in this case, emulation, we mean with this that this is a statistical approach that will evaluate a certain input and give the same output as a numerical model, but in this case, in a much faster way. And of course, there are different approaches to it. But in this project, we chose to go for machine learning, which is like a big thing these days, of course. But we're also now using it here in astrochemistry. And of course, I'm not the first one, or in our project, we're not the first one doing this machine learning, and this emulation approach has already been explored a little bit by, for example, the people of these papers. And inspired by these literatures, we basically continued or worked further with this approach. All right. Now let me, of course, again, there is struggles. I almost forgot about struggles. So what I was just saying, in our case, we want to try to model really a lot of chemical species, and we're using a chemical network that contains, this is the exact number, so it's more than 400 chemical species. And of course, then we're also still dealing with some physical parameters we need to take into account. So in general, we have a large parameter space. Secondly, we aim for a variable time step in our surrogate model. So let me show this a bit schematically. Let's say we build an emulator that is trained on a certain time step delta t. Then first of all, if we want to evolve the chemistry for smaller time steps, which probably will happen in our hydrodynamical models because there is like different time steps there, we cannot do that because the emulator is not trained on this, so we cannot use it on smaller time steps. And also, if we want to evolve it on more or longer time steps, then we need to stack these emulators together. However, of course, an emulator will never be perfect, so there will be a certain error if we use it once, and then if we use it multiple times, these errors can grow. So these are two aspects we want to overcome, and hence we came up with some solutions, again, of course, inspired by literature. So for the large parameter space, we'll use an autoencoder for this, and in a moment I'll tell you more about this. And then secondly, for the time step issue, we turn to using a trainable set of ordinary differential equations so that we get, in the end, a sort of differentiable emulator. All right, a lot of technical details, I know, but I'm trying to guide you through it. So let's look a bit more into this autoencoder thing. So what it basically is a way to reduce the dimensionality of a certain parameter space. So let's say we have our abundances n. If we build an encoder, we can encode this parameter space in a smaller vector z. If we then decode this again, we should be able to get the same output as we started with. In the case of autoencoders, there is a neural network behind this. So it's just a neural network that goes down in size, and then we can do the opposite for the decoder. And if we then train this type of neural network for the output to be, the input, to be produced also as the output, we have an autoencoder. Now this z parameter is in the jargon called the latent space. And so now we know we have found a way to reduce the dimensionality of our problem, but of course we still want to evolve the chemistry. And this we will do in the latent space. So what happens in the latent space, as already mentioned, there we use these trainable ODEs. So what are these? It's basically another differential equation, and we chose to follow this function, and this is also inspired by the function that is just used by the chemical kinetics, as you can see here. Now these tensors basically, or these terms, we will train this along the way while we're solving a differential equation so that we, in the end, have a product that these terms, that they fit the whole data we have at hand. So this brings us to the whole architecture of MACE, and I'll quickly guide you through it again so that hopefully you're following. So first of all, we start off with our physical parameters P, and then our set of initial abundances. In our case, we will concatenate these two, put it through an autoencoder to produce our latent space. Then for the latent space vector, we can train on certain time steps. We solve this latent differential equation. Meanwhile, we train the terms that I just shown to then predict what the evolution of these latent space vectors would be. If we then put this again through the decoder, we will get a prediction on the abundances after a certain time delta t. Now, if we then compare these predictions with the real abundances that we still have from all of our chemical kinetics data, if we compare it, and that's how, and in this way we can like train our emulator. All right, for the training, we explore two different methods. Basically, the first one is a local training scheme, and the other one is the integrated training scheme. So let me start with the local one. What do we mean with training in a local scheme? So in this plot, you can see just the abundance profiles of two common species, which are the black lines. And for the colored dots, you basically see, I hope it's a bit clear, these are the predictions after one time step by using MACE. So the number of time steps we use here is only one, and that's why we called it local, because we just only train on a local point in time. Now, if we have a look at the results of this, so here you can again see abundance profiles of different species. You can also see the error compared to what MACE predicts and what the classical chemical kinetics model does. At first sight, this looks pretty well because you barely see the dashed line underneath the dots, but there is a caveat to this plot. In this case, we only predicted the next time step. So for all of these radii or time, it's a bit the same. So we start from the real abundance that we know from the chemical kinetics, and we just predicted the next time step. And if we do that, we get a pretty good result. However, if we start off with the real abundances at the beginning of our outflow and just let MACE do the whole thing, you can see that we're diverging from our chemical kinetics models. Hence, we found that this local training scheme is not working to accurately predict the evolution of the chemical species in the outflows. Therefore, we turn to this integrated training scheme. And what we do in the integrated training scheme is also incorporate the chemical evolution in the training. So again, by the schematic, I'll try to explain how we do this. So instead of only predicting the next evolutionary time step of the chemistry, we predict a bunch of time steps. In this case, I show you here for 16 time steps, but you can increase this number or decrease depending on how good the results will be. So what do we basically do? So you see that some kind of hairs appear on our real abundance profiles, and we try to fit each of these colored hairs towards the black line. And hence, hopefully, the whole MACE system will have seen some chemical evolution, and this might hopefully, then it will be able, hopefully, to predict also the chemical evolution well. So let me show you the results. So this first plot is again the prediction of only the next time step if we start from the real deal. But we see that our integrated training scheme is able to predict this well. And then now comes the magic. Here you see the prediction when we start off just with the real abundances at the beginning of the outflow and just let MACE predict the whole evolution. And as you can see, the match is pretty well. And we were very happy with this result when we first saw it and almost couldn't believe it really worked. So I'm happy to show it here. So what we see is that, the abundances match pretty well. Of course, there's still a small difference between that. But as a very first result and sort of a proof of concept, which MACE is at the moment, this was very nice. All right, so the integrated training scheme seems to work. So what did we also do? I tried 9 different models, and I vary some hyperparameters. So in this case, I vary the amount of time steps I take in this evolution and also the size of the latent dimensionality. And what I plot here is an error metric, which is just the log difference of the abundances normalized. And I plot them in function of training time, because of course, in this big world of machine learning, computational costs are still very high and time is money and stuff like that. So what we actually aim for is, of course, to get a small error on our predictions, but also to do this in quite of a short training time. And hence, this corner here is the optimal spot where we want our final model to be. Now, there's also, the color bar, I didn't explain, but it's maybe clear here. So the colors indicate the complexity of the model. And you can already see for this integrated 9 model, it's more complex and hence it also takes more time to train. Now, there's also still a caveat to this plot. This error given here, this is an error of the predictions compared to models still. And as we all know, there's still also an uncertainty on models compared to the real world. Hence, in this case, it's not, these errors are already pretty decent for all of the models. So it's a bit unnatural to try to reduce this error to 0. As we know, the real models also still have errors compared to reality. Hence, in our case, we called this integrated 2 model as our best model in this proof of concept work, because it has a low error and can be trained in the shortest time. And for example, the integrated 8, for example, it's about the same error, but it takes a lot more time to train, and hence this is not necessary at this stage. All right, another last important aspect, of course, in the beginning I mentioned, the aim was for this emulator framework to be, of course, faster than the original chemical kinetics model. And hence I compared for a bunch of models what the time was to calculate it with MACE and what the time was to calculate just with the chemical kinetics framework. And we found an average speedup of a factor 26. At first, this might seem not too much, but we're pretty sure that once we also will implement this MACE framework in an hydrodynamics code, for example, we're aiming to implement it in Phantom, we can make use of the matrix implementation and make this very efficient, so that also because of, and now I'm losing my train of thought. So because of optimal matrix computations, we can still improve this speedup factor. And we haven't really researched it in detail, but the first few tests, we see that we can even increase this factor by another factor of 10 or maybe 100. So it's very, very promising. And then also still, so MACE is a proof of concept basically, and there's still much room for improvement on the performance side, for example. All right, this already brings me to my summary. So first of all, I think we all know, and that's why we're also here together in Melbourne, that we need to investigate these AGB outflows much more thorough than we're already doing, and there is really a need to couple chemistry with 3D hydrodynamics. In this talk and also in the paper, we show that the MACE framework is really capable of reproducing the evolution of chemical species using this integrated training scheme. Currently, we find a speed up factor of about 26, but we're sure that we can still increase this by a factor of 10 or even more by using this efficient implementation of and making use of matrix computations. There's also still other improvements possible that might increase the accuracy of the emulator. It might enhance the performance. And also, if we use some different approaches, we can also reduce the memory use of the emulator. And then lastly, we aim for MACE, or we developed MACE in such a way that it's flexible, not to be only used for AGB outflows, but hopefully other people in other astrochemistry communities, they should also be able to use it. Of course, you need to retrain it, because it's always a thing with machine learning, of course. You cannot just copy paste everything. You need to use the correct data. But we developed MACE in such a way that's made flexible to also be used in other astrochemical environments. With this, I want to thank you for listening. Please go check out my paper if I convinced you that this is a very nice project. And please come also talk to me afterwards if you want to have some more details. So thank you.
Very nice work. I have a question about the prospects. Have you already tried to couple this to the hydro?
Yes. I wish I could say yes, but no. So this is very fresh, let's say. But we're now testing just to use Chrome, so that you probably know Chrome, to use that in Phantom. So we're testing that out, and so that we can run some first models. But also the issue is a bit what I just showed, and the plots that I showed, the results, they're now trained on the one-dimensional models that we made. But these one-dimensional models, they evolve the chemistry with different time steps. And if you want to use it in the hydro codes, there the time steps will change. So we first need to make or build a new grid of models using the correct time steps before we can train MACE to then be still again applicable to
I see.
So there is still a lot of intermediate steps, but yeah, we hope to do this soon.
Okay.
Are there any differences in training time when you're looking at oxygen-rich or carbon-rich stars, or is it all the same?
That's a very good question. And I should be honest that we only did this on carbon-rich chemistry for now, but I suspect that the training time would be the same since the data is of the same form. And it's the same amount of, if you use the same amount of data, I don't really think that the specific numbers of the abundances would matter. So I expect this would be the same. But it's an important note because indeed, we can try to build just one emulator that can do both chemistry types, but maybe it can be better indeed if you train it separately. And that's all things you can explore. Yeah, hopefully someone will explore it someday.